Hello, our next speaker is Prof. Chengchao Huang. So Chengchao is Vice Director of Software Security and Trustworthiness Lab at Nanjing Institute of Software Technology, IJTCS. Chengchao's research covers algebraic and symbolic computation, especially for root isolation for transcendental functions and related complexity problems. Chengchao's recent work includes deep neural network verification, explanation, attack, and defense techniques for trustworthy AI. In this talk, Chengchao will tell us will give us more about the robustness analysis for deep neural networks from the perspective of modern learning. Thanks for Chengchao's talk.
Thank you, Cheng, and thanks for the introduction and thanks for the invitation. Yes, my network here is not very stable, so I did recorded a video in advance. So please help to play the video. Thank you.
In recent years, artificial intelligence has been widely used, and its trustworthiness has received high attention, especially for safety-critical applications. Today, I will present some research work of our group about robustness analysis for deep neural networks. From the perspective of model learning, we will show how to analyze the local robustness of deep neural networks in an efficient and effective way. The word robustness appears in quite many fields, such as biology, automation, control, and here, computer science. In general, we say a system is robust. That means it is stable. For deep neural networks, a phenomenon of unrobustness was discovered, that some invisible small perturbation to the input may lead to the wrong result, even for the networks with high accuracy on the dataset. This is also called adversarial attack. So, to analyze the robustness of deep neural networks under adversarial attack, the local robustness has been defined. The meaning of the word local here is mainly for the input space. The local robustness describes the property that a neural network's behavior is consistent in the neighborhood of a certain sample. Now let's consider a deep neural network for classification task. The deep neural network is a function mapping m-dimensional vector to n-dimensional vector. Each entrance of the output vector can be considered as the score of a class label for the input. So the label with maximal score is just the class that the deep neural network classifies the input into. For a given input x hat, we see the deep neural network is locally robust in the neighborhood B of x hat if all x in it obtains the same label from the deep neural networks. And a classical way to define the neighborhood is by L infinity norm. The distance from any x in B to the input x hat is upper bounded by a given radius r. Then the Rmax is the maximum robustness radius such that the property holds, which is an important indicator that reflects the robustness of the network. So the problem is how to compute it or estimate it. Now, let me first introduce some classical methods presented in recent years to analyze the local robustness of deep neural networks. The first class of methods is constraint solving-based verification. To verify a robustness property holds or not, the problem can be encoded into a SMT problem or a MILP problem. Then it can be solved by existing tools. So this class of methods are sound and complete. For the maximum robust radius, it can be computed by binary research on the radius. Namely, the exact Rmax can be obtained. Because the problem of verifying the local robustness is proved to be NP-hard, these methods have poor efficiency and unscalable for deep neural networks of large size. Moreover, these methods only support simple structure, such as linear or piecewise linear. The abstract interpretation-based methods is relatively efficient. The main idea is to use the so-called abstract domain to over-approximate the semantics of the neural networks on the input. So, it sacrifices the completeness in exchanging for efficiency. With the propagations in the network, the error will accumulate layer by layer. So the maximum robustness radius estimated by this method is always much smaller than the real one, especially for a large neural networks with many layers. Furthermore, it is still unscalable for huge deep neural networks since it needs consume a lot of time to maintain the shape of the abstract domain. Adversary attack can be also considered as a kind of analysis. When adversary example is found, the distance between it and the given input is the upper bound of the maximal robustness radius. However, for the region that's the radius less than the distance, we cannot provide any guarantee to its robustness. Recently, a statistical method is provided to analyze the local robustness with a probabilistic guarantee of confidence and error rate. It considers the event that the property holds or not to be a random variable. Then it can analyze the robustness by hypothesis testing via sampling. The problem of this method is that it cannot reflect robustness effectively, since for a high-dimensional input space, even a small error rate will allow a lot of counterexamples violating the property. So, the maximum robust radius obtained by this method is too large and meaningless. Let's see the figure on the right. The green part indicates the radii from the attacks, and the blue part are by this method. So, on the one hand, these methods have their own disadvantages on accuracy, efficiency, or scalability. However, on the other hand, the advantage of white box methods is they use models' information to obtain high accuracy and strong guarantee. The advantage of black box methods is they only use the inputs and outputs to gain high efficiency and scalability. This makes us think about whether there is a way to combine their strengths. The main idea of our method is to learn a model which is good enough to abstract local behavior of the original network, and then we analyze on the learned model. This is because properties can be transferred from one model to another if the two models are sufficiently similar. So the first question is, what is so-called a good enough model? In other words, how to measure the similarity between two functions. Here, we introduce the concept of probably approximately correct, PAC for short. For a function f, we say f prime is a PAC model of f if f prime approximates f by error bound lambda and error rate bound epsilon with the confidence at least 1 minus eta. Namely, the probability that f is bounded by f prime plus minus lambda in the region is at least 1 minus epsilon. Now we show what we actually learn in the context of our robustness analysis. Let's recall the definition of the local robustness. An input has a class label air implies that the air's entry of the output is larger than the others. So for such sample, we define the delta, we call it score difference, in which delta k equal to fk minus fl. Here we omit fl minus fl since it always vanishes. Then the local robustness is equivalent to that delta is always negative in the neighborhood, and the delta is just the function that we learn. Then, to analyze the local robustness in this way, the first thing is to learn a PEC model. Here we use a linear form of the input as a learned model. The technique for learning is called scenario optimization, which was used in the design of hybrid systems. Consider an optimization problem that we want to minimize the objective function under the constraints that fcx less than or equal to 0 on the whole region B. It is hard to be solved since it can be considered with infinitely many constraints. So, to solve this problem, we can construct another optimization problem, which has the same objective function, but contains only finitely many constraints on k samples in the region B. Then, it has been proved that if these k samples are obtained by independently, identically distributed sampling, and k is larger than this formula, then the solution of this problem can guarantee that the probabilistic of the constraint holds in the region is at least 1 minus epsilon with the confidence at least 1 minus eta. Now come back to our situation. It is not hard to construct the optimization problem. Since the learned model is linear, so the optimization variables are the coefficients of the linear form and can be solved by linear programming. Then we can obtain the PEC model. Then the remaining thing is to analyze the local robustness through the PEC model delta prime. Recall that the local robustness of the original model is equivalent to the delta x is always negative in the region. With the PEC guarantee, delta is PEC bounded by delta prime plus minus lambda. Namely, the delta plus lambda is a PEC upbound of the delta. So, we say the original model is PEC robust if the delta plus lambda is always negative in the whole region. Note that the delta prime is linear. More precisely, it is an affine function in the input. So the maximum point of delta prime in the region of a L infinity norm ball is easy to be found. That is, for the positive coefficients, let the corresponding variables to be x hat plus the radius r. And for the negative coefficients, let the variables to be x hat minus r. Then, by substitute the maximum point into delta prime, we immediately obtain the maximum and then we can decide its sign. Now, let's present the property verified in a more formal way. That is, for a deep neural network with a given region B, there exists a PEC model delta prime of its score difference function, such that for any x in B, we have delta prime x plus lambda is less than 0. So, our approach is sound to verify this property since we truly find a Peck model. Naturally, we also want to define a property for Peck unrobustness. Obviously, the property that exists x in B such that delta prime x plus lambda is negative, which is unreasonable, since Peck models are not unique for a function. That means there may exist a deep neural network satisfying both Peck robustness and unrobustness. Actually, we can see the complementary of the Peck robustness is that for all Peck model delta prime, there exists an input x in B such that delta prime x plus lambda is non-negative. However, it is hard to be verified, and even harder than to verify the restricted unrobustness for the original model, since the delta is a Peck model of itself. So the problem is how we can define a Peck unrobustness. Now, we define the Peck unrobustness in this way, that there exists a Peck model delta prime such that the probability of delta prime x minus lambda is non-negative, that is larger than epsilon divided by 1 minus epsilon. Of course, here epsilon is less than 0.5. Then we can show that this Peck unrobustness can imply the complementary of the Peck robustness. Note that the event that whether the delta prime x plus lambda is negative or not is independent with the event that whether delta x is less than or equal to delta prime x plus lambda. So, for Peck robustness, we can infer that the probability of delta x less than 0 is lower bounded by the product of the probabilities of these two events, that is 1 minus epsilon. Similarly, we can also infer from the Peck unrobustness that the probability of the delta x is non-negative that is larger than epsilon. Then our conclusion immediately follows. To verify the Peck unrobustness, we need to compute the probability of delta prime minus lambda being non-negative. Note that the region of this is one of the parts that a hypercube clipped by a hyperplane. Namely, it is the intersection of the half-plane delta prime larger than lambda and the L infinity norm ball B. Then, the property can be computed as the Lebesgue measure of the intersection divided by that of the region B. The Lebesgue measure is also called n-dimensional volume. At this point, we have finished describing our methods. We use the Peck model to approximate the original network, and then analyze the local robustness under the Peck guarantee. Then, let me show some experimental results of our methods. We conduct the experiments in 3 parts. The first is comparing the maximum robustness radii with the existing verification methods. The second part is to comparing maximal robustness radii obtained by our methods and that obtained by existing attack methods. And the third part is about efficiency. For the first part, we use both our Peck method, statistical-based method, and the abstract interpretation-based method to estimate the maximum robustness radii of 6 different fully connected networks for classifying the handwritten digital. As we expected, the radii estimated by abstract interpretation-based methods are very small, and the radii estimated by statistic-based methods are very large. Besides, a more interesting phenomenon is that under the maximum radii we evaluated, FNN5 shows stronger robustness than FN1 to FN4 and 6. However, the other two methods cannot discover this, which potentially shows that our method can reflect the local robustness of deep neural networks more effectively. Then, we also use the methods of adversary attacks, such as FGSM PGD, to obtain the counterexamples for these networks. The result is shown in the middle figure. By comparing our maximum robustness radii with the distances between the counterexamples and the inputs, we found that they are very close. Therefore, the minimum robustness radii estimated by our method have strong practical meanings under the PEG guarantee. To show the scalability of our method, we apply it on deep neural networks with large structures such as VGG and ResNets. Even for a huge network like ResNet 152, our method can efficiently analyze its PEG local robustness in about 3 minutes. We compared its running time with the GPU Poly, a parallel implementation of the abstract interpretation method. For the ResNet 18, our method only consumes about 100 seconds, while GPU Poly, supported by a more powerful GPU, consumes about 1,000 seconds. To conclude, we introduced an effective and efficient method for robustness analysis, which is based on model learning. The PEG model can be learned in a black box way, and the robustness can be analyzed with PEG guarantee. And we think the PEG model we got can be used to do many other analyses, such as explanation. The figures show a case of explanation via PEG model we learned. Actually, the main point of this report is not the concrete method we proposed, but the idea that we can analyze this huge system from the perspective of model learning. It is worthy to be studied and may be a promising way, especially for the complicated AI models. Okay, that's all for my report today. It has been my pleasure to share our viewpoint. Thank you very much to your kind attention.
Thank you, Chengchao, for this talk. I mean, it's really, I feel it's really very impressive work. And are there any questions for Chengchao?
Oh, hi. I have some questions. I think this is a pretty interesting work, and I'm curious that you use a linear model to approximate the original network. So is there any restriction on the network structure for this method to work?
We use linear model because on the one hand, the linear model is simple enough that we can analyze it. And on the other hand, in a small region, I mean a neighborhood of a sample, I think linear model is good enough to describe the behavior of the networks. So we use a linear model. Yes.
So first order approximation, right?
Yes, maybe for a big region that maybe a big radii, linear model is not enough to obtain a good enough approximation of the local behavior of the network. Yes.
Oh,
but in our situation, linear form is good enough, I think.
So and also in the experimental results section, I found that the results for FN 126 is not so similar. So is there any property of the network making common evaluation methods fail?
Sorry, I didn't hear clearly your problem.
So it's in the experimental results section. Maybe
let me show the. Okay. Yes.
So I found that for some of the network doesn't have good results for all the common evaluation methods. So is there any structures for this to happen? Any property?
I think our work is to verify the robustness. So we use a different structure of the FN and in experiment, and so I don't. Yes.
Okay,
maybe we can discuss the conference. Yes.
Thank you for your talk.